G'day everybody, welcome to today's lecture. I'm just going to start my recording. Welcome back to the second lecture for week 10, COMP2300. The topic we're continuing today is operating systems. We did a little bit of an extra tour into networks on Tuesday and then started off with this operating system topic. And so today we're really going to get into it and start to build your fundamental knowledge about how operating systems work both on your regular computers that you use every day, your desktops, your laptops, and your phones and tablets, as well as something like the Disco board and how you might go about implementing an operating system on that. I'm just going to make sure, hopefully all my sound and everything is working. Just view my screen for a minute. It seems like the sound's going in. It's not a crazy level or anything. I'm going to go to my small mode and then we'll just tour through the slides which we saw already in case you weren't with me on Tuesday. So we were discussing what OSs were, what kind of availability you had or what tools you had available to in an OS. And I think that the fundamental thing is to separate your graphical user interface, your mouse, keyboard, your windows and stuff, from what's actually the program, the core program of the OS, which is something which is organizing other programs to run on your computer. So making it easy for other programs to run. And we did discuss a few topics there. It would be a virtual machine. So it would provide a kind of environment for other programs to run on your computer, and be a resource manager. So it would give your other programs access to memory, access to processors, and would give them the ability to interact with hardware. So we'll talk a bit more about those things in a minute. And then I finished up by doing this little history of operating systems, going from the mainframe era where you didn't really need an operating system, you just needed something to make it easy to load individual programs. So you really wanted a sort of system monitor to make sure everything was going okay in between running big programs that would handle a lot of scientific or military or research data or banking data, for instance. Then as computers started to get smaller, there were some there were operating systems that were more, I guess it's not related to the smallness, but operating systems that let multiple people operate on one computer at once, so they'd be multitasking. And that sort of came about in the 70s. Computers started to get smaller. People had the idea that one person could just use one computer, so maybe everyone would individually have their own one. And starting with, in the 70s, there were some kind of proposals for what a workstation could look like, a computer that one person could use, with starting to explore graphical user interfaces as well, or user interfaces full stop. Then there were kind of personal computers which were much lower powered, much weaker, and really that was kind of a point where operating systems stopped being developed because the computer OSs were much simpler systems. And then in the 90s, the personal computers became more powerful, you could do more stuff, have real multitasking again, and that leads us sort of to today. And then there was this kind of big slides full of text about them. This is the thing the point that's interesting to me is that even in the 80s, when computers started to become very common, all of the classical OS features, this multitasking and management of memory, managing multiple programs at once, that wasn't in them. They were only going to do one program at once because the processors were too simple. But it didn't really, then it came back into it, came back to have those capabilities later. We're going to talk about a few, now we're in new content for this lecture. I want to talk about a few slightly more esoteric kind of operating systems or operating systems for specific tasks. So one of them would be a distributed operating system. So perhaps you would have a lot of CPUs in some kind of system, and every CPU would have just a little part of the operating system just to do communications, and then somehow the operating services are distributed over all of these CPUs. So it's a bit of a weird kind of idea, but it would allow you to take advantage of the fact that you had lots of computers in some system coordinated together. That's a bit of an esoteric one. One that's more relevant, I suppose, to everyday life, and particularly maybe rising in importance, is this idea of a real-time operating system. Real-time operating systems. So again, this is something a little bit esoteric, but normally when you're operating your computer, your operating system is handling the availability of the CPU to run bits of each program. So if you have 5 programs on your CPU, if you have only one CPU, only one of those programs can run at once. So the operating system is doing process management and allowing each program to have a go. Now you might like one of your programs to have a go on some kind of regular schedule. That is, maybe it is resident in memory at least once every 100 milliseconds or something. But in general, the scheduler of an operating system doesn't give you that guarantee. One of the regular processes on your computer could take too long, or it could just give your process a low priority and would never get back into the CPU, or something else could lock up the system, would never come back. But there are operating systems which are devoted to allowing a very high level of predictability under which processes can be run, so that you can guarantee that something does have access to the CPU on a regular time schedule. There's a lot of examples where this is incredibly useful. Things like the software that's used to fly a plane or drive a car, where if your driving software is kept off the CPU for 5 seconds, then your self-driving car operation would be in big trouble. Another situation where this is useful is actually in producing music with computers, as well as other kinds of media. When you think about how the bits get out of your disco board when you're creating sound, you're calling that audio sample play function whenever you want a sample to be set to the DAC. And actually that whole system relies on the fact that whatever calculation you're doing in your program is not going to take so long that the DAC doesn't have anything to play in between samples. So if you spend too long in your calculating what sample for your disco board to play, then actually you'll get errors in your sound, you'll get crackles or something where the DAC doesn't have a suitable sample to output. And the DAC is on a schedule, right? It's got to send out a sample once every 48,000th of a second. So if you're designing an audio system, you need to have samples ready to send to the DAC on this regular schedule, and so you need some guarantees that that's going to happen. And actually, when you're doing audio on a regular operating system, Linux, Windows, Mac OS, it doesn't matter, you don't have that guarantee. So the way to deal with this is that you hope, first of all, that your CPU is powerful enough to do all the processing it needs to do and provide samples to send to the audio output. And then you also have a buffer so that maybe you've got 5 milliseconds of samples available already processed. So you're processing 5 milliseconds ahead of when you need to actually send them to the buffer. So if the CPU doesn't give you that immediate access to the buffer to refill it when you need to, you've at least got 5 milliseconds grace period to relax without ending up running out of samples. And there are actually audio systems that have a different kind of OS. We might be able to talk about this a bit next week. A different kind of OS that provides some more real-time features so that you can be sure that every required time period your system has access to the audio hardware and can get those bits ready to send to the DAC. And then you can have a lower latency time between processing the audio and sending it to the output. So this is just a few situations where real-time operating systems will be useful. Music, as I said, robotics, right? If your robot is walking around and something unexpected happens, it needs to be in the be able to account for that data. This is an image from a research lab in Oslo where I used to work. I was doing music, but there were a lot of roboticists there, and they were using robotics for, or doing research in robotic surgery. So obviously you want your robotic surgeon to be able to react in microseconds to any unexpected events. And self-driving cars, of course, which is really important now, and we're starting to consider the implications of having much more automated everyday systems where our personal safety is reliant on these systems working. Self-driving cars is one example, but also things like apps that help us with our health. That's something which is becoming more common to think about. What level of reliability we need to, that we expect from these systems. So a few thoughts about real-time operating systems. What would you need for an operating system to be real-time? Maybe context switches to be fast. Maybe they should be small. Maybe they should quickly respond to external interrupts. Maybe they should be multitasking so you can handle lots of inputs and outputs. Maybe they should give you a low-level programming interface. Maybe they should be giving you inter-process communication tools. Maybe they should be very efficient and use the whole processor. These are kind of question marks. I think this is a bit of an Uwe slide. He put in a lot of ideas. Uwe Zimmer teaches real-time systems here at the ANU, so you might come back to learning a bit more about this as you advance in your education. Well, context switches should be fast anyway. Operating systems should be small anyway. External interrupts, it's not exactly that we need the responses to be quick, but we need them to be predictable. So there might be some external events that we need to have access to on a highly predictable and regular basis, and some that we don't need to have that access. Callum is saying in the chat, Callum's one of the tutors, that this is a big Uwe slide. This is a classic Uwe lecture about what the real meaning of real-time operating systems is. So it's not that you have quick responses to external events, it's that you know when it's going to happen. So if you need that access every 100 milliseconds, fine, you've got it. If you only need it every 1 second, that's fine. But if you need it every 1 millisecond, maybe we can make that happen too. So we can have very, very good control over, predictable control over time. Multitasking is kind of maybe a maybe a requirement, but it's not always. We don't have to be multitasking. We might be running just one very simple application. Every operating system needs to have a low-level programming language, so that's not really a focus in this particular scenario. Inter-process communication, well, almost all OSs need that as well, so it's not such a big, a particular requirement here. And then maybe we'd need some kind of redundancy or fault tolerance rather than using the processor completely efficiently. The core thing that real-time operating systems would give you is this kind of correctness of time, so you'd know when your results are coming in, but also making sure that you have some assurance that the results will be correct. I think this is a bit more of a 2310 topic, so those of you taking 2310s next semester will be getting a lot of information about how programs assure the correctness of results as well as correctness in time. And we need to have our results just at the right time, not too early, not too late. I guess the overarching idea here is that real-time systems need to be predictable and not exactly performant or fast. It can still be real-time even if it's slow. It's this kind of temporal predictability which is the most important point. Another kind of operating system would be ones that run on so-called embedded systems. So an example of an embedded system is actually your disco board. It's running a microcontroller, not a CPU. The difference is that the microcontroller includes the CPU and the memory and everything, many little features all on one chip, and it's designed to operate in a low power environment. So an embedded system is one that's sort of built into its intended application. It's just a part of some other hardware system. Like obviously there's some kind of computer which runs your refrigerator or your washing machine or your music keyboard and all of these, or your television, and all of these systems might be considered to be embedded applications. So often embedded operating systems do have real-time requirements, and they're also generally very simple. So the operating system that runs in an embedded system has to be small because the processor it runs on doesn't have much memory. It doesn't have a high level of performance. It's just designed to do exactly what it needs to do and no more, both for reasons of power utilization, cost of buying the components, and just being correct for the task. And these kind of operating systems don't usually have a lot of user interaction. So they're not going to have a GUI. They're not even going to have a way for you to send it messages other than maybe pressing the buttons on your washing machine. That's all of its user interaction it would be expecting. So the vast majority of CPUs in the world are in embedded systems, not in desktop or laptop computers. If you think about the devices in your house and around you that have a CPU in them, which are actually embedded, rather than being full, complete operating systems with GUIs, you start to have a very long list. I just started thinking of ones there, and I'm sure you could think of more. Even bits of your computer have embedded operating systems, right? Or embedded systems in them. Maybe they don't have an embedded operating system. Like your screen will have some kind of microcontrollers in it to give you the little on-screen menu. Your mouse probably has a microcontroller in it to connect to your computer. My keyboard has a microcontroller in it, my DIY keyboard. I know because I built it. My other music keyboards on my desk all have little microcontrollers. So there's embedded systems everywhere. They're just, the vast majority of computers are embedded systems. Taking a look around our house, all kinds of things could be embedded. I guess this is a slide that someone else made, and the question was how many OSs? Well, maybe there's 0 OSs, but at least there's a few embedded systems. Probably that one is embedded. The coffee machine might have some MCU in it. The fridge probably has a microcontroller in it with an embedded system. I'm not sure that the coffee grinders would. Maybe this one. Those ones have a little timer. So like you program it with the amount of coffee that should be coming out when you press each kind of button. So it would have a little micro in it to do that for you, but probably not an OS. So maybe it's a bit of a misleading slide in reality. So here's a big question. Are there standard features for an operating system? And don't say that it needs to have a GUI, because you know that I'm not talking about that. I'm not talking about operating systems in the sense of giving you a nice way to run Microsoft Internet Explorer. And in fact, all of those things that you might think of as features of an operating system, as in your web browser, your file manager, your text editor, your word processor, your IDE, they're not features of the operating system, they're applications running on your operating system, which happen to be included in the one that came with your laptop, or you purchased to run on your computer, or you downloaded from free as in speech, not as in beer websites. So there's no nice way to run Internet Explorer. I don't think so. Well, so what has the operating system actually got, which is a feature, and are they standard? So the answer is that there's not really a standard set of features, but we might be able to think of some minimum requirements to have something that you could call an operating system. So broadly, operating system can be a lot of different things. It could be something which is only 4 kilobytes, a very tiny embedded operating system, to the whole Ubuntu installation DVD, which would be 4 gigabytes, right? Or something even bigger than that. And these ones are so small because they're implementing only the bare minimum of what we need to be called an operating system. And these ones are so big because they're probably including a lot of applications, for one, as part of their installation medium. but also they might be prepared for running on a lot of different kinds of devices. So there might be many device drivers that are required. If you don't know what that is, we'll talk about it in a minute. They might have support for a lot of different languages and lots of data which needs to be included with it. So the operating system itself, the core of it, the kernel, might still be pretty small, probably bigger than 4 kilobytes, but still be pretty small. It's just all this other stuff that ends up coming along for the ride, applications, data, which needs to be included and which makes it so huge. But what are these minimum features? So we could almost say that there's a minimum set of features to be an operating system. I think when we were talking about the two roles of the operating system, as in being a virtual machine and giving access to hardware, the virtual machine part means that your operating system allows or presents memory to processors for them to use, that they're allowed to use for themselves. So this is this job of memory management, whereby individual processors don't get to access all of the memory on a computer. They just get a little slice. And in fact, they don't even get to see that slice. They don't get to see the real numbers. They get to see virtual memory addresses that are provided by the operating system and then translated into the real numbers by the memory management system. So that could be a minimal feature, some kind of memory management. Maybe not virtual memory, but at least some way that you can stop a process writing on the memory of other processes. Then you would have to have some system for managing multiple processes at once. So doing context switches, keeping track of all the processes on your computer together. That's really important. If you want your processes to be able to work together in any way, then they need to have some way of communicating. So inter-process communication is an important one. And then features for synchronization. The features like semaphores and mutexes that we were talking about a few lectures ago are something that the operating system would generally provide for its client process programs. So these would be kind of the features that we would consider essential in most operating systems. Another question, is there always an explicit operating system? Well, definitely no, and you've already experienced that because your disco board is not running an operating system. And the way your disco board is set up at the moment, it has some memory management features or capacities, but they're not being used very much, and they're certainly not used dynamically as your programs are running on the disco board. You don't have any capacity for different processors on your disco board right now, and these other things haven't been implemented at all. So unless you were writing things to memory explicitly, I suppose you could implement inter-process communication. No, so in this case, your development system, the disco board development system, is operating with just a standalone program. You turn it on, it runs one program, that's the one you've installed on it, and all of the needs of that program have to be supplied when they're put onto the disco board. So when you upload that program, it puts on it all of the parts of your program that need to work together. So we're going to talk about process management somewhat later, but the idea is that your computer needs to keep multiple things going at once. So when you write a program for Linux or Mac OS or Windows, you're defining something which will exist as just one process on a computer, and there'll be many other things going on at the same time. And the process, the OS has the job of making sure that every one of these processes gets a go of being the main event on the CPU, and then gets put on ice when it doesn't need to be in control. So it's keeping multiple of these processes going at the same time, while kind of tricking them to make sure that they never think that they've been to sleep and just woken up again to do their job. So that's tricky. We'll talk a little bit about what some of the issues with that, with process management a bit later. So now we've got a bit of a talk slide, but we're going to talk some more about processes now. But I just want you to consider what a task is on your computer, or what's involved in a task. What kind of data your computer would need to be running one process. I guess a process is kind of related to a task. So have a talk about that. I'm just going to see where we're going with this. Oh yeah. I'll sip my water while you're thinking about that. What does a process need on your computer? I'm going to bring up Teams for a minute. Oh man, I want to get rid of this, that one. I just want the chat. Ah, there we go. Yeah, so question is, what's a task? And Kit's answer was part of it. Tasks definitely need to have like a program to run. So they've got a sequence of instructions, which is their sequence of operations to run on the CPU. So that's the definition of a program, is this sequence of instructions. Have a sequence of instructions. That's the... Probably also have some memory to access, right? Oh yeah, here we go. We've got a detailed answer from Isabel, suggesting that maybe this could be not just the instructions, but some kind of collection of state information and context. I think context is a really important word. We were doing a context switch and finding all the stuff which was important to a program. So it's stack, it's flags, maybe it's registers, it's stuff in memory. So maybe there's some stuff that one task needs in memory that other tasks don't need. And maybe they also have some shared memory which needs to be worked on by multiple tasks. Yeah, so we're starting to see that, you know, each program is not, well, a program is not just its binary or its sequence of instructions. A task on your computer will also have the stuff that's important to it just at this particular time. So it's stuff that's got in memory, its stack, its memory of where it's up to in its sequence of instructions, so its program counter and other important register values, link register, stack pointer. So there's a lot of context that goes around just a work task on your computer as it's running, which our operating systems need to deal with. So let's have a bit of a chat about memory management now. So remember memory, we were talking about this, you know, some 6 or 8 weeks ago, discussing how your disco board programs can access all the memory they want. Now we did talk about how there was this memory map on your disco board, and not only that, the memory map points to a lot of different areas, and some of it is memory that you can always change, will be your static RAM on the disco board. You've got access to all of that. And we were sort of starting to wonder, well, what happens if you write something to memory and then another program comes along and just overwrites it? Is there any way to prevent that? And that exact problem is something which the operating system is helping you with. So the operating system will give you some, or put some limitations on how each program on a computer, each task, is able to access memory, so that the programs can share the memory and not take over other programs or rewrite them or mess them up. So the OS has this responsibility to make sure that memory is shared. Whenever it has a task, it will allocate some memory to that task, and hopefully it will be enough. And hopefully the OS has some way of increasing that allocation if the process is using a lot of memory. And then when a process is finished or a task is done, we've done the work, our program can quit, then the operating system should be able to say, okay, that memory is now unallocated, deallocated, and another program can probably use it. So the trick with allocating and deallocating memory is that your programs might like to have memory that's sort of continuous and makes sense, and whereas your memory map might be all confused. So in some sense your OS would like to make it nicer for the programs, and it certainly doesn't want to give programs access to memory that other programs are using. So we get to this concept of virtual memory where there'll be physical addresses on your memory itself, but the programs don't have access to that. The programs have access to some logical memory addresses which are given to it by the virtual memory system. So the programs themselves don't actually know where in physical memory they're located. They're just given some memory map, and then the virtual memory unit makes sure that that memory map connects to free memory on the physical system. And that is handy because it means that processors can't write on other people's memory, or they wouldn't even know where to go, how to write on them. It's impossible for them to input a physical memory address of anyone else's memory. Even then, processors generally are subject to some kind of memory protection. So even if they're in virtual memory segments, the computer makes it impossible for them to overwrite another program's memory or in fact read it. And obviously it would be bad for security reasons for both of those things to happen. If a process can overwrite another process's memory, then that would cause the other process to crash. And if a process can read another process's memory, that means that it could potentially spy on some important information, like your passwords, for instance, or some other secure data that process wasn't supposed to have access to. So it's important that the virtual memory system makes sure that each process gets separate memory, and we also have some system such that a normal process can't actually, or it's impossible for that process to write over another person's memory. Now, a question which you might start to think about is, well, if we've got a memory protection system, and that memory protection system is configurable, right? So you might be able to say, well, that bit of memory is read-only, that bit of memory is no access, that bit of memory is read and write for this process. Why can't the process then just talk to the memory protection system and say, okay, I would like to have access to everything, please. So there has to be some way that the memory protection system doesn't listen to some processors, but does listen to others. Because in fact, the operating system itself is a program running on the computer. So how does the memory protection system know the difference between the operating system and other processors? The operating system has to set up the memory protection hardware. It's actually a device as part of the CPU. But we need to make sure that only the operating system can talk to that and the other people, the other processors working on this computer can't. So we have this concept of privilege levels, which is an architecture level system built into your computer. That means that your OS can operate at a high privilege level or in some privileged mode, and your regular processors are running in an unprivileged mode. So the regular processors can't access the memory protection. They're physically unable to do so because of the way the hardware is designed, while your OS, when it's running in privileged mode, can access the memory protection system. Another memory management idea is that often our tasks might need to collaborate on some memory. So we would like to have some shared memory as well, or some way of giving two tasks access to the same thing. For instance, you might have if you're editing an image, for instance, you might divide some kind of filter into an operation that can be applied on a bunch of pixels at once, and then you might just generate 100 worker tasks to go ahead and fix every chunk of that image together. So they probably are operating on the same memory, even though they're multiple tasks. We'll talk a bit more about that stuff later. So remember about asynchronism as well. If we have multiple tasks working in the same shared memory, then they have to have this concept of synchronization in order to make sure that they're not splitting their reads and writes from that memory interleaved with other processes. We have to have some way of knowing that a process has been put on ice, gone to sleep. Meanwhile, some other process has changed memory while it wasn't looking. So the operating system will build in these features for doing semaphores, mutexes, context condition variables, other systems for inter-process communication to help us design programs that can access the same memory, access the same shared resources, things like devices as well, which are shared resources. And this will all be kind of built in with task switching and scheduling as well. So we talked a lot about that in the asynchronism lecture, so I'm not going to go into more detail there. And this is one other role for our operating system, which is crucial. Someone mentioned it in the chat just before, but it's called hardware abstraction. So remember in the labs when you were turning on an LED and you had to do a load, twiddle, store address for a million different things and it's impossible to remember? I hope you don't remember it because, well, if you do remember every single one of those little addresses you were doing in the labs, then you've got a special type of mind, and I respect that, but I can never remember them. I have to look them up every single time and go through very, very carefully. But thankfully, the operating system normally does all of that stuff for you. So it will abstract away the real work of setting up hardware, where you had to set a bunch of bits in a bunch of memory mapped registers. And it will give you what's called a device driver, which gives you some more kind of high level, easy to use interface to turn on an LED. So maybe when you're writing a program, you can just write one line which says set up LED, good. Another line, turn on red LED. So that would make your life much easier if you just had access to those two lines. And we kind of give you that within our labs when we've built little abstractions for those concepts. OSs will do a lot of other stuff to give you abstract access to hardware, particularly networking hardware, file system hardware, different networking protocols, everything else. So it will give you these application programming interfaces or APIs to work with all the different kinds of hardware that you could expect to work with when developing software for a computer. So now we're going to talk about what a kernel is. Finally, someone mentioned kernels on Tuesday. So the kernel is the program, the main program which forms the core of your operating system. So it's the program which runs when your computer turns on, the main one which is going to be doing all of the OS roles, doing all of this scheduling, doing all of this memory management, providing these device drivers in some way. And it's just a program. So the way that kernels behave in a computer is that they will run your programs for you, start them running, let them go, and then your other programs will get to access different stuff by asking the kernel. So there's something called a system call that a program can run on a computer, and a system call gives that program or tells the kernel that that program would like it to do something, and then the kernel provides a service or access to some memory or peripherals on behalf of that program. The program itself that's running in a task never really gets to have direct access to all the memory and peripherals. It just asks the kernel to do it for it. So it might say, I'd like some more memory, please. And then the kernel is like, okay, you get this memory. Or it might say, I'd like to turn on the LED, please. And the kernel is like, it's done. So the kernel gives you this interface to those hardware interactions, as well as software interactions through system calls. Where's that go? Oh, we're talking about that in a bit. We'll talk in more detail about system calls. So we have a little break for an analogy time. Analogy time with Charles. Maybe we should have some music or something for analogy time. Anyway, we're not going to do music, but oh, I could do some music here. You probably can't hear it. Turn it up. Analogy time with Charles. So the first analogy is like how to think of the kernel as a program on your computer. And I'd like you to think of the kernel as being a kind of like, exactly what I think you can hear when you see the word kernel. It's like a corn kernel, right? It's like a nut. So it's something that your computer has got all of these important functions bundled together. And it gets them all bundled together, and it can just use them to have a very small program that does all this important work and lets you do all these important tasks together. Okay, that's the first analogy. Second analogy. Your kernel is kind of like a bridge, okay? So it's not like a nut now, it's like a bridge. And the two things that it's connecting as a bridge, is your hardware and your software. So this is the hardware abstraction part. So as a bridge, your programs now don't have to be doing crazy reads to memory map registers. They can just run a simple command and have access to all the hardware they want. And also, you know, I mean, taking the analogy a bit too far, if you wanted to cross this river by yourself, your program wanted to, maybe it would be dangerous, right? So the bridge gives you a safe way to cross it. You're not going to break your hardware or get it into an inconsistent state where it can't continue to run. And then we got our final little analogy for what an operating system is. Our final little analogy is a share plate. Okay, so what does a share plate give you? Well, it means that everybody at a party can have equal access to some kind of food. And that's what the operating system is going to try to do for you. It's going to try to make sure that every program running on your computer has some kind of equitable access to device drivers, to memory, and to all of the other system resources on your computer. Okay, there was my little analogy time. So the three things that's important. Your operating system is a kernel. It's the core of all of these important programs to make sure your computer can keep running. And it's a small target. It should be something which is compact and fast. It should be a bridge between hardware and software. And it should be a share plate. So each of your programs can have equal and nice access. Oh, there's something going on in the chat. I'm really not sure what you guys are on about right now. Schnidge? Schnidge? Don't write about schnidges in your in your exams. I certainly am pushing my luck with those analogies. Okay, we're back in real mode now. We're going to talk a little bit about system calls. I guess this is an info thing. If you want to find out what a real system call is like, of course you can just have a look at the syscalls header file. Can't you also just go like manual syscall, man syscall, is that a thing? Man syscall. Yeah, indirect system call. So you can come and see what all of your system calls are in here. Linux system calls. A big list of all the system calls there are in Linux. Some are available and some are not. You can change the ownership of a file. You can change the mode of a directory, change directory. These are all system calls. So they're ones to interacting with your operating system. Ones for interacting with files. fopen is in there somewhere. Fork, that's one for making a new process. I'm not much of a system call knower, but you know, if you guys go out there, you folks get out there and become super high level Linux hackers, then you can learn all about all of these. malloc is in there somewhere. Oh no, that's in the C library. Yeah, so you can find out all about the system calls. And then if you wanted to be a real hacker, you can write your own system call. So there's the instructions for the Linux kernel of how you would go about it. If you wanted to write your own system call for Linux, there were calls that you feel are needed and are not there, then you can add one and make a submission and see how you go. I'm sure that might be a bit of a process before it's accepted by the Linux kernel developers, but you could develop your own fork of the Linux kernel and do that. So OSs are probably complicated things. We're going to talk a little bit about the structure of an OS, the structure of a kernel, and how the different approaches that could be taken. So a kind of simple structure for a kernel is to have, or for an operating system is to have what's called a monolithic structure. And the idea here is that you have a lot of a lot of the operating system kind of built into the same program, built into the kernel. So you've got quite a giant kernel, not a simple one, that includes a lot of features that can't be changed out and designed to all work together and be really efficient. So there are some good things about this. As I said, they can be really efficient because if you're just designing one program to be your whole operating system, a monolithic program, then you can optimize the heck out of it, right? You can make sure that everything is working together in the absolute most efficient way. And in fact, many early operating systems, particularly ones for personal computers, consumer computers, were absolutely monolithic operating systems. And they didn't have any other choice because they needed to run on very weak hardware. So it was absolutely required that the authors of those operating systems got every single ounce of performance that they could out of the hardware to make sure it was a good experience for users. So here's a list of things that are monolithic OSs. Most early Unix systems, we haven't even talked about Unix really, but we will in a minute. MS-DOS, the old Microsoft text-based system from the 80s. All the Windowses before Windows 2000 was like the main game. So there was, as I said before, there was kind of two parallel lines of Windows going for a while. There was Windows 95 and Windows NT. And Windows NT was not monolithic. Windows 95 was. They were available together on the same day. You could get two kinds of Windows, and they actually weren't completely compatible. This is in the late 90s. All of the Mac OSs until version 9. And the idea of this this monolithic system is that it's all one program. As it gets bigger and bigger and bigger, it can be really difficult to maintain. It can be really non-portable, so it makes it much harder to add support for different kinds of hardware. For doing that bridge task, every time you do that bridge task, you have to add more stuff to the program to make sure that your software can talk to the correct hardware. You're going to end up in this system with all of the services of your OS, things like all kinds of inter-process communication, all of the stuff it's providing, all the device drivers, all the interaction with hardware, they'll be part of the kernel. And as a result, they'll have the same privilege level. And for many computers, there are sort of levels of privilege that your system can have, and there are multiple of them. So the kernel might have the highest level of privilege, and then it might give out somewhat less levels of privilege to other services. Another option, it would be something where you've got a monolithic OS, okay, but it allows you to have some software modules loaded and unloaded. And this is good because it means, for instance, if you want to support a lot of hardware, different kinds of hardware could have different modules developed for them. So you might have modules for dealing with running with one type of audio output, one type of video card, one type of disks, file storage devices. Different kinds of architectures might have extensions with different modules. And you'll still have all these things living in the kernel, but the modules will be easier to maintain because you can write a new module when you have to encounter some new hardware, make sure that module is working really well, and then add it into the OS. And this is exactly how Linux works at the moment. The Linux kernel has what's called kernel modules that you can load in. Generally, you don't mess with those, although if you're running Linux on a laptop with some strange hardware, you might have started to explore which modules are required to run your hardware. And if, for instance, you've got an NVIDIA video card, you'll have some choice of different NVIDIA video drivers with modules, as well as an open source driver. So that's monolithic and modular. Then another kind of quite different idea is this idea of a microkernel. So rather than having all of the stuff, the important stuff in your operating system living together in the kernel, one huge program, you make your kernel as small as possible. And it's going to try to put any other kind of service outside of itself. So we'll have a lot of different modules that will live in a lower privilege mode, operating outside of itself. And all of these modules, tasks, and services are then going to have to talk to each other through some kind of inter-process communication. So some things that we might have expected to be part of the operating system are now just kind of a regular program in an unprivileged state, existing on the same flat platform as the other tasks. So there's lots of true microkernels are kind of rare. There's lots of interesting research projects, things like L4, Minix 3, which is a famous one, that are microkernels, the Mark microkernel, an old one which ended up getting turned into the kernel for Mac OS. Used to be a microkernel. I think it's now more like the modular monolithic model. So there's some things in between modular, monolithic, and microkernels where there's kind of a hybrid approach. So people start to design OSs that take some cues from the microkernel approach, or they're implementing an open source microkernel and then adding a lot of features to make it more practical, I guess, for present computer systems. Yeah, so that's microkernels. Now we're finally going to talk about Unix. I've got a few slides here about Unix. And I've got one meme slide. So Sip. I had to have my sip every time I have a meme slide. So the meme slide here is about Jurassic Park from 1993, the famous movie, based on a famous book. But in Jurassic Park, there's a scene where the kids are escaping from the dinosaurs and they end up at some computers. And this young person sits down at the computer thinking, oh my goodness, we've got to do something to escape from these dinosaurs. And then she says, this is a Unix system, I know this, which is hilarious that we have Unix as part of like pop culture. I don't think it would be mentioned in pop culture anymore, but why is that important? Well, Unix is kind of, it's two things. It was a kind of operating system developed and sold in the past, in the 70s and 80s. It doesn't really exist now as something you can buy, but it's served as a standard way of doing an operating system that's been inherited by a lot of other operating systems. Good examples are Mac OS and Linux, both operating systems which are not Unix, but they inherited a lot of the ideas and operate in broadly the same way now, and even run a lot of the same software because they are both inheritors of this idea. So if you know something about Unix, then you know how to use a lot of different operating systems. So when she sits down, she says, oh my goodness, it's Unix. I'm going to be fine. I can now save us from the dinosaurs. So what's the deal with Unix? Another little history lesson. Well, in the late 60s in America, there was a famous research laboratory called Bell Labs, Bell being the telephone company. And they were working on operating systems and computers. And there were a couple of researchers there. Now what's his name? Ken Thompson was there making operating systems that would be implementing this time sharing idea and have multiple users, had some great ideas. And they started to have the idea that they could write an operating system not in assembly language dedicated for a particular computer, but in some kind of higher level language. And I think in the Bell days, they were working in a language called B, which was now like lost in the midst of time, or it's not used anymore. And then somewhat after leaving Bell Labs and ending up, I don't know where they ended up. Or maybe they ended up at Bell Labs having left somewhere else. I've got the story mixed up. Ken Thompson was working with another person called Dennis Ritchie, and Dennis Ritchie brought this idea for a new language, which they ended up calling C, which was the language that they would write Unix in, or as a starting point, it was their operating system for their system they were making. And the cool thing about Unix was once it was based in C, you could then run it on a different computer by compiling it for that computer with a different C compiler. And that was something which was a bit new. Generally, every mainframe computer, every different kind had its own operating system, every different model. So it's like if your MacBook Pro ran a different operating system to an iMac. That would be crazy now, but we have this idea that at that point in time, computers were so expensive and so huge, there were so few of them that every model could probably have its own operating system written directly in assembly language exactly for the instructions that were needed. So now that was one innovation. Once it's written in a high level language or a high low level language, we can port it between computers. Unix had a few other cool features which people found useful and are still true today. It had this idea of a file system which was hierarchical. It's difficult to now believe that you could have a non-hierarchical file system, like you could just see all the files at once on your computer system. But that was another option in the past. Now hierarchical file systems are normal. There's this idea that in Unix that everything is a file. That's like a meme about Unix. Everything's a file. Files are files, of course. Directories or folders, they're also a file. A directory is a file that contains a list of the files that are in it, some of which can be other directories, including files. That's how we have a hierarchical file system. Hardware devices, they're files. Unix has two different kinds of files for hardware devices. Some that are like streaming data into you, like a keyboard streams data in character by character, and some that you can access the whole thing. So like a disk, you could grab a say, give me, byte 1000, and it would give you the correct byte. Inter-process communication, that's also a file in Unix. You can have what's called a named pipe, which is a kind of place you can put some data, and another process can receive it. Another idea is called sockets. That's also a file in Unix. A socket is a file that you can, again, put data into, and some other process can get it, but that process might not be running on the same computer. It could be running on a different computer connected by a network connection. So that's cool. In Unix, the Unix operating system can make more processes, and processes can make more of themselves. And they always do this by making a clone of themselves and then changing it. So they always fork or clone themselves and then make a new process. Yeah, so there's Leopold's just mentioned POSIX, which is an important Unix word, POSIX. It's the definition for what Unix is, the standard definition for how to make an operating system. It's not called Unix because at the time that they made this standard, or the IEEE Computer Society defined this standard, Unix was kind of a copyrighted word, so it was a brand name. So it's not something that you could just call your thing Unix. That was owned by a company. Yeah, you can read about that history another time. The way that Unix will work when you log in is that or when the computer starts up, first thing that happens is a program called init runs, starts your computer. That's running in the kernel mode. That runs a program called login. That's also running in this privileged mode. You type your username and your password, and then the Unix operating system will run a program on your behalf, owned by you in the user privilege mode, which is called your shell, your command shell. And then you can enter your commands. So we're used to command shells living in a window like this, but command shells can also be kind of the main program that you get to interact with it in your computer. You can still see one. I think I probably will break OBS if I just go into text mode on my computer, but if you're on Linux, you can press Control F3. Don't do it if you don't know how to get back to your your window manager, but that will give you a text shell to start interacting with your computer. And there are lots of Unices or Unix-like systems. All this long list, notably including Linux. That's a flavor of Unix which arrived in the 90s, and Mac OS, which is a flavor of Unix that was developed based on another flavor of Unix called BSD, which was one of the early ones. Now we're going to talk a bit more about privilege levels, and I'll even show you how it works on a disco board. So we talked a bit about how your computer is going to stop some processes writing in the place where they shouldn't. So your operating system is a program running your computer. Another program is now running, and the operating system wants to stop that program from writing over some memory that it shouldn't be writing over. So we need to have some concept of abilities for different processes to access certain bits of hardware, and the abilities for the operating system to set those access controls. Now on your disco board, we don't often, so far you haven't dealt with privileges, and I don't think you really need to that much in this course. We set it as kind of a thought exercise for now, and maybe an extra exercise in Lab 11 to think about privileges. But on an operating system, you would normally have some graded privileges, right? Your kernel would have the most privileges, and your device drivers would have maybe less privileges, but still pretty high, and your applications would have even less privileges than that. Of course, we don't want applications to read each other's data. We've gone through that in every way possible. But we probably also don't want our application code, which a regular programmer could write, to then start interacting directly with devices. Why might we not want that to happen? Well, if I write a program which directly starts talking to my, sorry about clicking my microphone there, if I start a program which directly starts talking to my video card, I might talk to it in the wrong way, and then my video card might stop talking to the rest of my computer, and then none of my programs will be able to display stuff on the screen. So we have to be careful about how we interact with hardware, because if it goes wrong, everything else on the computer goes wrong with it. Similarly, we definitely don't want applications to be able to change things in the kernel. So if your applications, well, my mouse is not working very well today, or my arm is not working very well today to control my pen, so I'm drawing very poor arrows. If my applications could rewrite the kernel, then they could just say, rewrite the kernel such that the kernel then gives them all the privileges and lets them talk to the other applications. So we definitely need to have methods of cutting off access to the operating system and the hardware from our regular applications. Now we're going to talk a bit about how this works in the disco board and in hardware, because it turns out that to do the concept of privilege levels, you need to have hardware support for it. It needs to have hardware support. So you need to have some concept such that such that an instruction can only be executed in a privileged mode. So some instructions, for whatever reason, whether they're particular loads from particular places in memory or other special things, that can only be executed once we're in a privileged mode. And the hardware has to enforce this. So it has to be that if you send this instruction in your program, the hardware literally is like, no, I'm not going to do that. Otherwise, your programs could just rewrite the kernel, rewrite themselves, take over the operating system, end of security, end of everything. Yep, Adam Rallander's made a very good point. That would be a hacker's dream, applications rewriting the kernel. That's exactly what, that would be the hacker's dream. Generally, that's not possible. The applications often can only rewrite other applications. But if the hardware is going wrong, if there's problems with hardware such that you can trick the kernel into running arbitrary code, then that's the end of your expectations about security. Leopold's just said hardware hackers come into play. Yeah, if as a hacker you can attack the hardware somehow, attach little wires to the CPU, then you could potentially cause big problems with these expectations about security and privilege. So, what about on disco boards? What about in ARM v7m? On disco boards, you tend to have two kinds of privilege. Privileged and not privileged. We've actually got two concepts of privilege on the disco board, which are kind of on the axes of this graph here. There's the privilege level, and then there's two modes. Now, thread mode is the mode that your normal code is running. So when you're running a regular program in your disco board, whatever runs under the main label, that's in thread mode. And handler mode is entered when you're in an exception handler. So as it turns out, on the disco boards, the design is such that whenever you're in an exception handler, that's running in privileged mode. So all handler mode code is running in privileged mode. Regular old code can either be running in unprivileged mode or privileged mode. The only way to change whether regular mode is with regular code is in unprivileged or privileged mode is to be in the exception handler. So the exception handler can set and say from now on you're in privileged mode, even though you're running regular code, and then the code will continue. So once you're in privileged mode, you can control some things like what code is going to be executed, have control over memory reads and writes, and in particular access to memory mapped peripherals. Your Disco board doesn't have what's called a virtual memory unit, so it can't give processors a new map of memory to keep them safe in a safe area, but it does have what's called a memory protection unit, which can stop unprivileged code from reading from certain locations, reading and writing from certain locations in memory, which you can learn about as an extension if you want to. There's a chapter from this interesting book, The Definitive Guide to the ARM Cortex-M3 and Cortex-M4, which gives you some details about how the memory protection unit hardware works on your Disco board. And it's something that you can play with in week 11 and 12 in your lab if you want to. It would be great to get that running and do have some fun with it. Some good things that you could do with the MPU, it's a little bit hard to see here, but your MPU could, for instance, make some SRAM read-only, so you could make sure that like your program data was not able to be overwritten. You might also make a little bit of your SRAM at the bottom of the stack inaccessible, so that if your stack tries to go further than that, then you would know about it. You'd end up with an exception. So that would help you protect yourself against stack overflow, which would be good. So we can use this hardware to make a safer place for our software to run. But what I'd like to do whoops. What I'd like to do is, for the last few minutes of this lecture, have a go at running what's called this supervisor call instruction on the Disco board. So we're talking about the idea of our... Oh, lost my mouse here. We're talking about the idea of your operating system having a system call. So you would get some way of talking to the OS. And this is the way we do it on the Disco board. If you wanted to make an OS and you wanted to have a way of an individual unprivileged process being able to talk to the OS, it would have this, you would use this supervisor call instruction. So we can look this up in the reference manual. And the supervisor call instruction is a simple instruction that has 16 bits and includes an 8-bit immediate. So the idea would be that you might define a bunch of system calls up to 8 bits, so you could have 256 of them. And then each one of those would be, whenever you run SVC with that number, that system call would get run. And what happens when you run SVC is that you actually end up in a exception handler. So calling SVC, the supervisor call, puts your Disco board into handler mode, running some handler code that's you've defined already. So we can see how this is done in a minute. What's going on here? I'll talk a bit more about it. You can also have this deferred supervisor call. So if this is set, then the pend SV handler will be called according to usual interrupt exception rules, so that you can make a supervisor call which is going to happen after some other stuff happens. So it's just deferred a little bit. It's not going to happen exactly immediately. And now I'm going to see how it actually works on your Disco board. So it's not very hard. I've already done it, basically. We've got our SVC handler, just like when you're writing another handler, you just have to, or in our system, all you have to do is overwrite that function. If you were writing an operating system, obviously your operating system would not allow application code to overwrite the handler codes, because all of the exception handlers should be handled by the operating system. So in this case, here's the handler for the supervisor call code. And when I want to run this supervisor call, I just type svc and then the argument. In this case, I'm going to say 7 is the argument, okay? So this triggers the svc handler. And interrupt the So let's just see what happens and prove to ourselves that this is going to work. Put some nops in there. And I'm going to try it on my disco board. So here I am in my main program. I've only got one instruction to run, svc. And I immediately end up inside that, that svc handler. Now here's the trick. The idea was that my svc command, instruction, would give me some way to define different activities. So the operating system might have a table of different routines to run for each one of these numbers. Number 0 might go to one routine, number 1 would go to another routine, number 2 would go to another routine. And the question now is, where's the 7? So my 7 was here, and now I'm here, and I don't have it. It's not in my registers, and it's not on the stack. So where is it? And actually, in this design for this particular chip, the way that you get back that number is to actually dig back into the instruction stream and just actually read it straight out of memory, straight out of your program. So that 7 was written somewhere, and you can only do this as an immediate, so you have to go back and find it. So how are we going to find it? We have to get our program counter back, because our program counter has been changed by the interrupt. It's going to be on the stack, so we have to get it off the stack. And then we have to get that number, which will be just somewhere near from where our program counter left off. So first of all, I'm going to get the program counter back. So I'm going to letter R0, and I want to get something off the stack. It's near somewhere nearby on the stack. And I actually just happen to know that it's offset by 18 bytes on the stack. Whenever you've got an interrupt triggered, the stack puts your program counter, and all of those caller save registers get saved onto the stack, and I know that you have to go back 18 points to get it. Yeah, it does seem super hacky, Adam. I mean, there's different, Adam's just commented that it seems super hacky. Well, there might be other ways to do it. Maybe Ben Gray is going to walk in the room in a minute and tell me I'm doing it wrong, but this is how I learned to do it. It will work though. So now we can get PC into R0, and I don't want to load PC if I, for instance, type R1 load R0. This is now, whoops, here's PC. I want to load the PC into R1. I'm going to end up with the instruction after that, which will be this branch instruction. I don't want that. I want to get one just before it. So the 2 bytes, is that correct? I really don't, well, we'll see what happens. I might just load 1 byte. Let's see where we get. Oh. So I ran my supervisor call, ended up in the handler. I'm going to get my PC back into R1. R0. No, that doesn't seem right. What did I do wrong here? just remember on my other screen I had my example I was going to run. Oh, whoops, it's not 18 bytes, it's OX 24 bytes. Whoops. Run my supervisor call. That looks right. That's something in the program, the data area, the program code area. Leopold's a bit confused about the NOP, just to have some space. Don't need them at all, actually. Sometimes when I'm running in debug mode, I just put some NOPs everywhere that I'm going to end up so that I'm sure that the debugger will land somewhere. Because if you have a handler with just the label and then the BXLR, it will just go straight to the BXLR and run that code and skip through it. But I just want to make sure it stops right there, just so that we've got a bit of space. So it's not necessary. It's just for demonstration purposes. So now I'm going to run. I've got PC. I'm going to load 2 bytes before that into R1, and there we go. We get 7. So that's our method of getting back our value from the supervisor call command. There's other architectures even ARM architectures, where the supervisor SVC has like a way when the interrupt is called that the arguments end up in registers, but that's not in ARM v7M for the Cortex-M4. It's just this very simple method of getting the argument of a supervisor call. So naturally, if you had an OS for this, the implementation of that OS would have to take into account that this special way of doing system calls is necessary. Yeah. Now there's a little bit more stuff about processes and scheduling we're going to talk about on Tuesday, but I think this is enough for today. We've gone through our whole 90 minutes. And I'm going to say goodbye to you all in a minute, but I hope that everything is going well with assignment 3 and the week 9 labs. Assignment 3 is a lot of fun, and you start to really have to get deeply into the hardware of your disco board and thinking about which pins do what. I haven't had much time to look at them, but I've seen a lot of Piazza posts going by with pictures out of the reference manual, and I can see people are really getting engaged with it, which is just wonderful to see. It's great that the tutors are able to help you out with those things and give you a lot of help in labs. I think a lot of people have appreciated some different approaches we're taking in the labs. The tutors have figured out better ways to run them, to make sure that everybody in the lab gets to participate in calls as concepts are being explained, and I think that goes a long way to helping everybody out. I guess I was worried a few weeks ago that people would have trouble finding little wires. And I guess the good news is that, for me, is that no one has complained about not being able to have little wires. So if you're in Canberra and you're desperate for some little wires, I've got a stock here at my house. You'll have to send me a private message and we can arrange to get them to you. But I think it sounds like everyone's got them. I'm really a bit worried that we'll get to a few days before the assignment and find that some people don't have their little wires. But we're really trying to make sure that the message is out there, that everyone has them available. Oh no, Daria. Spent half an hour trying to figure out why code was not working. Spent half an hour trying to figure out why code wasn't working. Apparently my wire wasn't working. Oh no, that's terrible. Yeah, the hardware errors are the bane of a programmer, because sometimes you expect that everything on your computer is working fine, and if something's wrong, it must be your fault. And so far, that's always been the case in assembly programming, but you do now have some situations where your little wire could be plugged into the wrong place, or it could be broken, or it could be a cheap one which is not making a good connection. So the issues are going to be a little bit trickier to debug sometimes, but just make sure you take it slowly and check everything twice as you're going through. I'm sure that you will all work it out and have a great time. So I might roll to the outro, and looking forward to catching everybody on Tuesday for the thrilling conclusion of operating systems and the start of our final topic, which is architectures. So catch you all then.